Quantum mechanics is weird because despite the fact that we're celebrating its 100th anniversary right now, we still don't understand it. What is really going on in this, our best, most important framework for doing fundamental physics? We understand on the basis of quantum gravity why the Earth moves around the sun or apples fall from trees, but we don't understand what happens when gravity becomes strong, like in a black hole or near the Big Bang. So basically, nature uses every trick that it can think of to make physics work in interesting ways, and it really does give physicists a sense of accomplishment at the end of the day to figure it all out. I'm Sean Carroll. I'm a physicist and philosopher at Johns Hopkins University, host of the Mindscape podcast, and also author of a bunch of books, most recently the Biggest Ideas in the Universe series, including Space-Time in Motion and Quanta and Fields.
How does quantum mechanics work?
I like to think if you were a physicist circa 1895, okay, the very end of the 19th century, you would have been forgiven for thinking that we were almost there. We were almost having a complete theory of nature in our grasp, because they had the idea of particles, right? The idea of an atom was a little bit sketchy to a lot of physicists in the 1800s, but they eventually caught on, and they were beginning to realize that atoms were made of other particles, protons, neutrons, electrons, and so forth. And then the particles, which make up matter, are pushed around by fields, by the electric field, by the magnetic field, by the gravitational field, and so forth. So you have this sort of two-part harmony. Matter is made of particles, forces come from fields, and all the effort in the future of physics would be figuring out what are all the particles, what are all the fields, and then you'd be done. There were a couple of clouds on the horizon. One of them ended up being relativity, the fact that the symmetries of Maxwell's theory of electromagnetism were different than the symmetries of Newton's theory of classical mechanics. But the others were that there were certain properties of matter and materials that didn't quite seem to make sense. And I'm going to be ahistorical now. Let's pop forward to like 1911. They were putting together the picture of the atom that is the cartoon you've always seen, right? There's a little nucleus at the center of the atom, and electrons are circling around it like planets orbiting a star. This is called the Rutherford atom model, after Ernest Rutherford, who was a brilliant experimental and theoretical physicist. And this was entertained, and people liked the idea that electrons were kind of like little planets, but they instantly figured out it can't possibly be right, because that electron orbiting the nucleus would give off electromagnetic waves. It's a moving particle. Moving charged particles give off light. All of the light you're looking at right now came from some electron in motion, moving around. So you can calculate. You can say, if the electron is moving around in orbit around the atomic nucleus, if it gives off light, it will lose energy and spiral into the nucleus. How long should that take? And the answer is every atom in the universe, including the ones in the chair you're sitting on or even in your own body, should collapse to a point in 1/100th of a billionth of a second. So that clearly does not happen. The idea that electrons are like little planets in a solar system is just wrong. And this and other things, black body radiation and other experimental results, convinced people that there wasn't this clean division between particles and forces. They said there's aspects of light, which is supposed to be a wave, which are particle-like. Einstein said that. There are aspects of particles, like electrons, that are wave-length. Louis de Broglie, following work by Niels Bohr and others, said that. And this whole thing coalesces almost exactly 100 years ago, in 1925, in the theory of quantum mechanics. And almost right at the same time, two different versions of it came out. Werner Heisenberg had his version called matrix mechanics. Erwin Schrödinger had his version called wave mechanics. They showed that they were actually mathematically equivalent. But quantum mechanics, I like to say, it was the second of two big ideas in the history of physics. The first big idea in physics was classical mechanics. Relativity is a pretty big idea, but not as big as classical mechanics or the second big idea, which is quantum mechanics. Quantum mechanics throws away classical mechanics and replaces it with something very different. It says that electrons are not particles or waves. They act like waves until you look at them, and then they look like particles. That is a very, very difficult thing to swallow, and physicists are still trying to figure out what to make of it. It's so much fun reading the history of how these ideas developed, because today we're just taught the final result, but they didn't know what was going on back in the early days. In 1926, Erwin Schrödinger presents an equation for what we now call the wave function. It's a dopey name for a very important idea. So think of that little electron, instead of orbiting in a circle, it's a wave. It has a profile around the center of the atom. And the equation works very well. It's still the equation that we use today, but then you have to ask, okay, semi-philosophical question, what is the wave function? What is it telling us? And Schrödinger thought, well, okay, in some cases, electrons act like waves. In other cases, they act like particles. Maybe the equation says that if you start with an electron wave all spread out, it will sort of localize itself near some point and it will look like a particle. Turns out not to be true. The equations don't care about your feelings. It's the opposite. If you start out with a localized electron wave, it will spread out all over the place. So it was yet another physicist, Max Born, different than Niels Bohr, who pointed out the right way to think about Schrödinger's wave function. He said, think about what happens when you measure a property of the electron, like its position or its velocity or whatever you want to measure. He says, what the wave function is doing is it's telling me the probability of getting a different measurement outcome. In particular, if you want the math, you square the wave function. That tells you the probability of seeing the electron somewhere. And this was just bizarre and crazy for all sorts of reasons. People didn't like the idea that probabilities were involved at all. Of course, there's probabilities when you flip a coin, but that's just because you just don't know everything there is to know about the coin. Since the time of Newton and Laplace, we thought that physics, deep down, was perfectly deterministic. And here's Max Born saying, no, it's not. That was difficult to swallow. But the other thing that's difficult to swallow is, why in the world is the idea of measuring or observing something showing up in the fundamental laws of physics? That had never happened before. Of course, you have to think about measuring things and observing things, but it was always imagined that if I measure the position of a planet or something like that, in principle, I can do that measurement completely benignly without disturbing the system in any way at all. And what Born is saying is that when you measure an electron, you instantly and dramatically change its wave function. And to tell me what the fundamental laws of physics are, according to what became known as the Copenhagen interpretation of quantum mechanics, after the city where Niels Bohr and Werner Heisenberg and others were doing their work, part of those fundamental laws are a set of rules that say, here's what happens when you measure the properties of a system. So quantum mechanics is the only theory in the history of physics that has rules about measurement outcomes and has measurement playing an important role in what those laws are. And if you ask, well, what is a measurement? What counts? Do I have to be conscious? Can a video camera do a measurement? The answer is, we're not going to tell you the answer to that. We don't have an agreed upon set of criteria for when a measurement happens. And this is known cleverly as the measurement problem of quantum mechanics. There's various plausible resolutions to it, but we don't agree on what the right one is. Very often in physics, learning physics, teaching physics, doing physics, it's very helpful to visualize things, either precisely or maybe in some toy kind of metaphorical way of doing things. But we have to keep in mind, it's not necessary that there be an accurate way to visualize certain things. We have to accept that the world is not here to make things easy for us. So when it comes to the wave function of quantum mechanics, we're a little bit stuck. There are simple cases, like if you have one electron and that's it. No other particles, you're talking about the wave function of one electron. You can actually visualize that. If you just think about space as two-dimensional to make your life easy, the wave function is a function. You're cheating a little bit because rather than having a value, it's a complex number. That means to say a real part plus I times an imaginary part, where I is the square root of -1. But okay, who cares? What you need to know is there's a profile, there's a shape. There's basically a value at every point in space which says this is the wave function of the electron at every point in space. So go ahead and visualize it. If you ever took chemistry class and you saw those images of what are called orbitals in different kinds of atoms, those are literally pictures of wave functions. Those are values of the wave functions of different shapes the wave function of an electron can take in an atom. But just to show you that the universe is not going to always go that easy on you, sometimes you have two electrons that you care about. And one of the most profound features of quantum mechanics, which separates it from classical mechanics, is that you don't have a wave function for electron 1 and a separate wave function for electron 2. Because remember, the job of the wave function is to say, what is the probability that I measure something, right? So when I have two electrons, I can have the probability of seeing one electron anywhere in the universe, and I also have the probability that I see the other one everywhere in the universe, but they can be connected. Maybe I know that the electrons are 1 centimeter apart, but I don't know where they are, right? If I measure one of them, then I instantly know where the other one is, but I don't know ahead of time where either one of them are. This is the phenomenon called entanglement, and what it means is that rather than having one separate wave function for one particle and a distinct one for the other one, which would mean there's no connection between them, the wave function tells me the probability of both particles at once. Mathematically, if you want the details, you assign a complex number to every pair of positions, the position of particle 1 and the position of particle 2. You want to visualize that? Good luck. You're not really going to be able to do it unless you can visualize complex functions in 6-dimensional space. But that's what it actually is. We can write it down and we can deal with it and we can go back to what things look like when it's just one electron if we really want to visualize things. But at some point we have to trust that the equations know what they're doing. You would think from the name quantum mechanics that quantum mechanics has something to do with quantum, which is a word made up to denote a discrete amount of stuff. It comes from the fact that in the early days of inventing quantum mechanics, when you had radiation coming from hot radiating bodies, or when you had electrons in orbits around atoms, there were discrete possible energies you could observe. Light is absorbed at certain frequencies by a gas and not at other frequencies. When an electron changes energies inside an atom, it goes from a certain energy to another one without being in between, without sort of continuously evolving from one energy to another. So there was this idea of a quantum jump from one state to another. But that discreteness is not fundamental to quantum mechanics. It's not built in. It's not because quantum mechanics says the world is discrete, it's made of pixels, it sits on a lattice, or anything like that. It's because the opposite. Quantum mechanics is a story of waves, but sometimes waves only vibrate with certain discrete sets of frequencies. Think of a string attached at two ends, like on a guitar or violin or whatever. You can pluck the string, and given the tension of the string and the distance between the ends, it will vibrate. It will give you a certain note. But the same string is also able to vibrate at twice the frequency. There's the fundamental frequency where the string vibrates as a whole up and down, and there is the next overtone where it sort of vibrates half and half on different sides. And then a harmonic series. There's a way that the string can vibrate so it goes up and then down and up again. That's 3 times, and so on. So a discrete set of possible frequencies comes out of the motion of a continuous string vibrating. And likewise, the continuous wave function in certain circumstances can only vibrate with certain discrete frequencies. And so that's why electrons have discrete energies in atoms. Now, quantum mechanics is a framework, just like classical mechanics is. Classical mechanics doesn't say what the world's made of. It gives you the fundamental rules, and you pick out, oh, the world is made of particles or fluids or whatever, and here are the forces acting on them, and you plug that into the framework of classical mechanics. Quantum mechanics is the same way. Most of what you talk about when you first encounter quantum mechanics, electrons and photons or whatever, you're applying the rules of quantum mechanics to particles. But we've known, since the time of Maxwell at least, that there are also fields, right? There's the electric field, the magnetic field, the gravitational field, maybe there are others. So we can also apply the rules of quantum mechanics to fields. And lo and behold, we get what is called quantum field theory. Quantum field theory then is not a replacement or an improvement on quantum mechanics. It's just the rules of quantum mechanics applied to fields rather than particles. And what happens is you take a field. So a field is the opposite of a particle. A particle has a location. A field exists everywhere, but it has a value at every point. So the electric field is a little arrow at every single point in space. It has a direction and a length. And then you say, okay, that's a field. I'm going to apply the rules of quantum mechanics to it. So I'm going to invent a wave function for the field. And I'm going to say, what is the probability the field looks a certain way, doing certain things? And the math just goes through exactly like an electron sitting in an atom. There are certain discrete vibrational frequencies of the field. And that shows up in particle physics experiments as particles. The field vibrates a little bit, you think you're looking at one particle. If the field vibrates a little bit more, now you think you're looking at two particles. And you can match up exactly the mathematical descriptions on both sides. So the resolution to this early mystery of quantum mechanics, why do electrons or photons behave like particles sometimes, behave like waves other times? The answer is, number one, they're waves. That's what they are. They are waves in a field. Not only is there an electric field and a magnetic field, there's an electron field for the electron particle. There's a neutrino field. There's a quark field. Everything is made of fields. But number two, when you apply the rules of quantum mechanics to fields, they show up in our experiments like particles. So this is why it explains this distinction that things act like waves when we're not looking at them and appear to us as particles when we do. If we think back to that late 19th century physicist who thought matter was made of particles, forces come from fields, what happened to that guy? Like, where is he now in the world where everything is actually fields, but they look like particles when you apply the rules of quantum mechanics to it? Well, it turns out there are two different kinds of fields, fermions and bosons. And the difference is, are you allowed to stack up vibrations of the fields on top of each other to let them vibrate more and more? That's what you're used to, right? If I have a violin string, I can pluck it a little bit, I can pluck it a lot. That is what we call a bosonic field. Boson fields can pile on top of each other. But fermion fields have this slightly interesting property that there's only one kind of vibration at a time going on in the field. In the particle language, we say that in any one region of space or in any one quantum state, we can have as many boson particles as we like. But a fermion takes up space. Fermions can only be one at a time. If you go back to your chemistry class again, why can't you put all the electrons in the lowest orbital? There's a rule called the Pauli exclusion principle that says that for any one shape of an atomic orbit, only one electron can be in there at a time. Technically, it's two electrons because it can be spinning clockwise or counterclockwise, but that's the basic point. Fermions take up space. So the reason why our 1898 physicist thought the world was made of particles and fields is because really it's made of fields. But those fields can be bosons or fermions, and fermion fields kind of act particle-like. They cannot pile on top of each other to make a big classical field like electricity or magnetism or gravity. The 20th century in physics, it'll still be considered an amazingly important time in the history of physics. We're still teaching physics 1,000 years from now. The 20th century will be remembered. Not only did we invent relativity and quantum mechanics, but we figured out what particles and fields there are, at least the ones that make up you and me. You know, we started circa 1900. We were trying to understand atoms. We realized there's a nucleus, and around the nucleus there are electrons. And then we realized that the nucleus is not indivisible. It's made up of protons and neutrons. Skip forward to the 1960s and 70s, and we realized that protons and neutrons are not elementary particles themselves. Each proton and each neutron contain 3 quarks. And the way it works is, a proton has electric charge +1, a neutron has electric charge 0. There are a kind of quark called the up quark, which has charge +2/3. and a kind of quark called the down quark, which has charge -1/3. So if you sit down there at home and try to figure out how can I make a proton, how can I make a neutron, you'll quickly figure out a proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. And that's a pretty good picture right there, but it becomes complicated by the fact that particles change identities sometimes. This was, again, an exciting thing in the early 20th century, radioactive decays, right? If I have a neutron all by itself, it can decay into a proton and an electron. It doesn't quite work because certain things like energy are not conserved. We eventually figured out there's another kind of particle called the neutrino that is created when a neutron decays. Really, a neutron decays into proton, electron, and anti-neutrino. And how's that happening? Well, neutron has 2 down quarks and an up. Proton has 2 ups and a down. Inside the neutron, one of those down quarks converts into an up quark by spitting out an electron and an anti-neutrino. So that's a pretty good picture. We have 4 different kinds of matter particles, 4 different kinds of fermions, up quarks and down quarks. Those are both inside protons and neutrons. And then we have electrons and neutrinos. Okay, you think that maybe that's your complete picture. Then we discovered, all the way back in the 1930s, a heavier cousin of the electron. This is called the muon, and famously there was a physicist at Columbia, I.I. Rabi, who said, "Who ordered that? We did not know why the electron needed to have a heavier cousin involved." But now we know it's because this idea of the 2 quarks, up and down, and the 2 non-quarks, which we now call leptons, the electron and the neutrino, that pattern is repeated 2 more times. So there are 3 families of particles. There's the up quark and the down quark, but then there's heavier cousins, the charm quark and the strange quark, and even heavier cousins, the top quark and the bottom quark. And then on the lepton side, we have the electron and a neutrino associated with the electron, which we cleverly call the electron neutrino. We have the muon, its heavier cousin, and a muon neutrino. And then we have a tau particle, which is heavier than the muon, and a tau neutrino. 6 quarks, 6 leptons, arranged in 3 families. And all of these particles, these are all the fermions that interact via bosonic fields. We have, of course, the electromagnetic field, we have the gravitational field, and then we have the nuclear forces. Inside the proton and neutron, there are gluons, which carry what we call the strong nuclear force. The gluons hold particles together, hold quarks together in the protons and neutrons. And that conversion of the neutron into a proton, electron, neutrino, that's the weak nuclear force. It is carried by particles called the W and Z bosons. So that's more or less the picture. That was the picture of all the particles that we discovered up until a few years ago. We have 6 kinds of fermions. We have 4 kinds of forces. It turns out that to make the whole thing fit together, we need 1 more particle, which is, of course, the Higgs boson. The Higgs boson is not really a force-carrying particle, but it's not really a fermion either. It's part of a field that exists all throughout space, and the other particles are kind of swimming in it. The other particles, like the quarks and the electrons and so forth, feel the influence of the Higgs field, and it affects their properties like their masses and their charges. So the Higgs field was finally discovered in the form of the Higgs boson in 2012, and that, as far as we know, is all the particles that we're able to produce here on Earth. This puts together in what we call the standard model of particle physics. And if you do an experiment here on Earth, it is so far, to date, 100% compatible with the standard model of particle physics. We look outside and we see that we need dark matter and things like that. Dark matter doesn't seem to fit into the standard model, so we're optimistic that there are more particles we haven't yet discovered. But right now we're doing a good job of fitting the data that we have. If you think about the standard model, it's on the one hand amazing. Like everything fits together like a really tightly constructed jigsaw puzzle. Everything matters, everything is doing some purpose, etc. But on the other hand, it's kind of baroque and almost ugly in some ways. So many particles, random looking kinds of masses and interactions for those particles. We would like something a little bit prettier. In fact, most of the particles in the standard model don't play a role in your everyday life. And that's simply because there's a feature that if you have a heavier particle, a particle with large mass, it will be able to and want to decay into lighter particles. The only thing that stops it is there are quantities that are conserved, like electric charge and spin and things like that, that you just can't get rid of. The total number of quarks in the universe is conserved, for example. So the electron is the lightest particle with an electric charge, charge -1. The proton is the lightest stable particle that has a non-zero total number of quarks inside. The neutrino is the lightest particle that has spin, a half spin unit, as we say, that makes it a fermion. And turns out these are basically the particles that make up us. There's also the neutron gets thrown in there because when you combine a neutron and a proton, you can make a stable nucleus. But if you think about the charm quark, the muon, the tau whatever, the top and bottom quarks, the Higgs boson, all these particles just decay away. They were there near the Big Bang in the very early universe, but then they decayed into lighter particles. Those lighter particles assemble into atoms. The atoms turn around inside stars and make heavier elements, and ultimately they make us. So you don't need a lot of the ingredients of the standard model to explain you. You are made out of up quarks, down quarks, and electrons, held together by the strong nuclear force and electromagnetism. That's 99.99% of understanding you. You need to understand some details about the masses and the Higgs boson and things like that. Gravity is important, but it doesn't require that much. And what's interesting is, of course, you can imagine, and particle physicists love to imagine, that there are new fields and particles we haven't yet discovered. Dark matter in the universe is the best evidence that we have directly. There must be some particle we haven't yet discovered in order to account for the gravity we see in galaxies and the universe. We don't know what the dark matter particle is. We know how much dark matter there is and where it is. We don't know what kind of particle it is, but we know it doesn't interact with you and your body. How do we know that? Because there are rules for what happens when one particle interacts with another. And if a certain particle could interact with the things you're made of, the electrons, the protons, and neutrons, then we would be able to make it in the laboratory. We would just smash other particles together, watch what comes out, and the dark matter would appear. Indeed, this is particle physicists' favorite thing to do, look for new particles by smashing other ones together. We haven't found anything by doing that is not already in the standard model of particle physics. So there almost certainly are new unknown particles and fields out there, but they're either too energetic to make in our best particle accelerators, they're too massive, it just takes too much energy to create them, or they only interact with ordinary matter so feebly, so weakly, that maybe there's a chance of making one, but we don't notice. Either way, you are made of electrons, protons, and neutrons interacting through electromagnetism, gravity, and the nuclear forces. One super fascinating thing about the way the physical world has arranged itself is this phenomenon we like to call emergence. The idea that the air in this room, I could describe by saying, well, it has a certain density, a certain temperature, a certain velocity perhaps. But I know deep down that it's made of atoms and molecules. But I don't need to tell you the position and velocity of every atom and molecule in the air to tell you useful, interesting things about it. We can have approximate but really, really good descriptions of things based on wildly incomplete information about them. I can predict the motion of the Earth around the sun without knowing the exact position and velocity of every atom in the Earth. So this is a good news, bad news situation for physics. We know the particles that you and I are made of. We know what is called the core theory of physics. The core theory is basically Einstein's theory of general relativity for gravity plus the standard model of particle physics. And that core theory suffices to underlie all of the physics of the everyday world. That's the good news. There's two pieces of bad news. One piece of bad news is it's hard to go beyond that. We know that this theory is not the final answer. We're not saying that the core theory is the theory of everything. It doesn't explain the Big Bang or black holes or dark matter, etc., okay? The other piece of bad news is, in principle, it does account for chemistry, biology, psychology, politics, who knows? But in practice, that's completely useless information. If you want to be a biologist, knowing about the top quark is not important to your life. Even knowing about up and down quarks is not that important, despite the fact that there are protons and neutrons in nuclei, and there are nuclei in atoms, and there are atoms in biological organisms. If you want to study biology, your best bet is to study biology, not to study particle physics. So I think it's incredibly significant how the different layers of reality depend on each other. And we know one layer really, really well, the layers of particles and forces at the level of quantum field theory and atoms and things like that. We would like to do even better at that layer, but we understand it very, very well. It leads to the layer of chemistry and atoms. The stability of the chair that I'm sitting on ultimately comes down to the rules of quantum field theory. Those atoms and molecules come together with electricity and magnetism to make all of chemistry, which is a pretty big deal. Chemistry comes together to make biology, and so up on the ladder. We can both appreciate that these different levels depend on each other, while appreciating also that to study them and to understand them, we need to take each level seriously for its own sake. Physics is not just a set of true facts and equations and things like that. In many ways, it's kind of an attitude. It's a way of thinking about different things. So it can take you very far. You can talk about the physics of different kinds of things, all the way up to the physics of society. You can model social groups or voting or things like that using very similar ideas to statistical mechanics and other ideas that came about in the 1800s. So there should be and is a close cross-pollination between different disciplines. There's a whole department at my university, Johns Hopkins, called biophysics, because physicists and biologists working together is an incredibly useful endeavor. Having said that, that doesn't mean that all ideas in physics are useful to biologists, and in particular, the ideas of the Higgs boson, or the mass of the top quark, or spontaneous symmetry breaking in the strong interactions. These are not that interesting to biologists, and they don't need to be. They're specific ideas. They're not general techniques. The closest I could come to saying how useful is it for a biologist to know a little bit about the core theory of physics is kind of in a negative sense. There are things you might plausibly imagine could be important to biology, but the physicist can come along and say, no, that can't work, it violates the laws of physics. I'm thinking of something like bending a spoon with my mind, right? We could imagine that I have the powers of telekinesis. I can use what's going on in my mind, which after all, the brain is very complicated. We don't really understand a lot about how it works. Maybe it's possible that it could give rise to some force that could push things around without me touching it. The laws of physics are here to tell you that's not going to happen because we only have a few ingredients. We have gravity, we have electromagnetism, and so on. We know certain limits on what is possible. If you're an engineer, you might be a very, very clever engineer. You're not going to design a rocket ship that can travel faster than the speed of light. You're not going to build an engine that runs with no fuel input or energy input forever. You're not going to build a perpetual motion machine. You're not going to violate the rules of conservation of electric charge and things like that. So sadly, physics puts limits on what we can do that are a little bit more narrow than what we can imagine, but also it suggests new ideas for things that might be possible, and those can lead to some big surprises. By the middle of the 20th century, physics was in a funny kind of place because we had the idea of quantum mechanics. We even had the ideas of quantum field theory. It was in the 1940s, early 50s that people like Richard Feynman, Julian Schwinger, Shinichiro Tominaga figured out how to tame the problems that quantum field theory seemed to have. When people first invented quantum field theory, it gave nonsense answers for very simple questions like what is the probability that two electrons bump into each other. So Feynman and his friends figured out how to fix that, but it was really only for electromagnetism. That was the one force of nature that we really understood at the quantum level. We knew there were other forces. We didn't know about quarks, but we knew that protons and neutrons were kept together inside the nucleus of an atom. And in fact, we had hints that there was something called the strong nuclear force and the weak nuclear force. So what were they? Well, an obvious thing to do is to say, if electricity and magnetism work so well, let's just generalize the idea underlying electricity and magnetism, which is something called gauge symmetry. Symmetry of rotating fields into each other at different points in space and time. So this is what Yang and Mills did. They said we can go from electromagnetism a la Maxwell to a whole bunch of other kinds of theories that are different but similar. Maybe one of them describes the nuclear forces. The problem was, in electromagnetism, the existence of that symmetry predicts something very noticeable, namely the photon has zero mass. It's a massless particle. Being a massless particle means the force associated with that particle extends very far throughout space. And indeed, the two massless particles we know about are the photon of electromagnetism and the graviton of gravity, both of which give rise to long-range forces. But the nuclear forces are not long range. They're confined to very short distances inside the nucleus. So other people said, well, it can't be a similar gauge principle like electromagnetism. It has to be something different. It turns out that indeed both the weak nuclear force and the strong nuclear force are due to gauge symmetries, much like electromagnetism, but nature hides them from us in very clever ways. And I like to say this is because the universe loves us. And the reason why the universe loves us is because it uses every possible trick in its book to construct the standard model of particle physics to make it the most rewarding it can be when physicists figure it out and when graduate students have to solve those problems. So basically, if you want these massless particles to not give rise to long-range forces, there's two different ways to do it. One way is made use of by the strong interactions, and the other way is made use of by the weak interactions. In the strong interactions, it's the gluons that are carrying the strong nuclear force. They are massless particles, but they don't stretch out to infinity because they keep bumping into each other. The strong nuclear force is a strongly interacting theory, so the gluons just zoom around in circles, bumping into each other inside the protons and neutrons, and you can't pull them apart. That is why that force is short range. For the weak nuclear force, it's the Higgs boson that is doing the work. The Higgs boson fills all of space and basically confines the weak nuclear force by absorbing it. The lines of force from the W and Z bosons, which would want to stretch out to infinity, get eaten up by the Higgs field that is all around them. So basically, nature uses every trick that it can think of to make physics work in interesting ways. And it really does give physicists a sense of accomplishment at the end of the day to figure it all out. Quantum mechanics is weird because despite the fact that we're celebrating its 100th anniversary right now, we still don't understand it. We use it, we put it to work with amazing success, whether it's building Large Hadron Collider or building like a semiconductor device in a consumer electronics thing. Quantum mechanics is there, tested, very, very reliable. But remember, it has this idea that when you measure something, it changes the state of the quantum system you measured. And you haven't told me what it means to measure something, the measurement problem. So, of course, the most obvious example of measuring something is when I, as a conscious human being, actually make a measurement of something. So it was perfectly legitimate and absolutely tempting, let's say in the middle of the 20th century, to wonder out loud, does this mean that consciousness plays an important role in the fundamental laws of physics? Now, all I can tell you is I don't think so. I think very much the other way. I think the consciousness arises out of the ordinary interplay of all the complicated things going on according to the laws of physics. But there is a school of thought that says actually consciousness is responsible for the collapse of the wave function in quantum mechanics, or maybe I shouldn't even think about wave functions as real things. I should think about agents making measurements as the real things, and I use quantum mechanics as a tool to predict what their measurement outcomes will be. So on the one hand, I have my opinions about what the answer to these questions are, but on the other, and even more importantly, I think we don't spend enough time and spend enough brain power addressing these questions. We've kind of swept them under the rug. There's this whole field called the foundations of quantum mechanics. What is really going on in this, our best, most important framework for doing fundamental physics? And I like to sort of semi-joke that if you were to tell somebody who didn't know anything about it, oh yeah, we have this wonderful theory of the world, but there's a part of it which we don't understand, we're still struggling with that, they would think, oh, it must be that trying to understand that stuff is the single most important goal in physics. That the people who are specializing it are the glamour scientists who are stolen away by the best universities with huge salaries and so forth. Whereas the reality is the opposite. If this is your specialty in physics, you'll find it very, very difficult to get a job. Most physics departments don't want to think about the foundations of quantum mechanics because they can't figure out a way to make progress by doing experiments. So I'm glad that people have crazy ideas about the foundations of quantum mechanics, even if those crazy ideas somehow bring consciousness into the mix. I don't think that's ultimately the way to go, but we're not going to figure it out unless a lot of smart people put a lot of effort into doing so. I've said before that the late 19th century physicists would be forgiven for thinking that they were almost done. They almost had it completely under control. By the way, very few people actually did. You can find one or two quotes from physicists of the era, but most physicists are a little bit more cautious than that. In fact, some were very explicitly saying, no, we're not done yet. Hang in there. It's happening again. Right? Now, over 100 years later, we're in a situation where we have a theory, the Standard Model plus general relativity, that fits all the data that we have. But we know it's not the final answer. You'll find zero physicists today saying that we have the complete theory. They might have different opinions about how close we are to having the complete theory. There's several obvious reasons why we know we don't have the complete theory. Dark matter in the universe is the most obvious experimental result. Even though we haven't detected dark matter in the laboratory, we've seen its effects in the sky. We can't fit it into the standard model, so that's evidence that we can't be finished with particles and fields yet. On the theoretical side, I said that we have gravity and we have the standard model of particle physics, but we only understand quantum gravity in a very limited regime where the gravitational field is relatively weak. We understand on the basis of quantum gravity why the Earth moves around the sun or apples fall from trees, but we don't understand what happens when gravity becomes strong, like in a black hole or near the Big Bang. This is the problem of quantum gravity, and it's experimentally inaccessible at the present moment. We know what energy you would need to have at a particle accelerator in order to make quantum gravitational effects become obvious, and it's way, 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 way bigger than what we can possibly do here on Earth with present-day technology. There was this moment in the 1980s when there was a lot of excitement about what is called string theory or superstring theory, and the excitement was entirely warranted, because people made the relatively bold conjecture that instead of particles, you should imagine that the fundamental units of matter are little loops of string, and just follow your nose, plug that into the rules of quantum mechanics, see what happens. And what happens is absolutely amazing. Number one, you inevitably predict gravity, which is important because gravity exists. Number two, you inevitably have the room for everything else, for all of the fermions and bosons and all these fields that we see in the universe. So the idea of a single unified theory of everything seemed very attainable. And they were very excited in the 1980s, continuing on in the 1990s. String theory, as it is called, is still a very, very promising approach to unifying everything we know about physics, but we have completely failed in connecting it with experimental data. We were hopeful. Back there in the 80s, people said, okay, let's calculate the mass of the electron according to string theory. Turns out to be much, much harder than we ever anticipated it would be. And maybe that's because string theory is not right. We don't know. Maybe it's because nature is just not being kind to us this time. So I think that today, far fewer physicists would try to predict how close we are to the fundamental theory of everything. I think there needs to be a fundamental theory of everything because there is the universe. There is the real world. The real world does something. The theory of everything is just the list of everything the universe does. And that may or may not be easy for us human beings to figure out. The Three-Body Problem is this fun TV show based on these wonderful novels by Xijin Liu. And there's a lot of interesting ideas that are related to physics and cosmology that come up. I'm not going to give you any spoilers or anything like that. But I've consulted on various TV shows and Hollywood films and things like that. And people always want to know how realistic the physics is. And I say, most often, like the unrealistic physics is that the star wakes up after sleeping in their bed and their pajamas are not wrinkled. Like that is completely incompatible with the laws of physics as I understand them. But it's this process of doing science that is really unrealistic in a lot of shows. And the three-body problem is no different. A big plot point in the show is that scientists have discovered that there are data coming in that are incompatible with their theories. And they sort of panic and they don't like it. And they commit suicide or they quit physics or whatever. This is exactly the opposite of what would happen in the real world. There's nothing better in physics than when your theory is incompatible with a new piece of data, especially a theory that has been working very, very well for a long time. Now, if you are individually the person who came up with the theory, you might be sad. But as a community, that's how you make progress. If you want to win the Nobel Prize in physics, you don't show that Einstein was right. You show that Einstein was wrong. That's the way to get people excited. And for whatever reason right now, we're in a situation where in fundamental physics, in cosmology, gravity, particle physics, our theories are almost too good. Our theories are fitting the data really, really well. It's very different than the situation 100 years ago when we were chasing all of these new surprising experimental results. That's when you can come up with better ideas. The space of possible theories of physics is way too big to just guess the right answer. We need guidance from experiments. And the kind of guidance we need is unexpected results. So the only way to do that is to build bigger and better experiments, and that's what we're trying very hard to do right now. It's an almost inevitable temptation to think that when we build better computers, whether it's literally quantum computers or just much more effective artificial intelligence algorithms, that will help us doing physics, that will give us new ideas, maybe new input from somewhere. I'm, on the one hand, super optimistic about the usefulness of quantum computers and AI as tools in physics, and at the same time pretty darn skeptical that it will lead to new conceptual breakthroughs. What computers are really good at doing is solving well-posed problems. So in mathematics, for example, if you have a theorem and you want to prove the theorem, this is a lot of what mathematicians do, prove theorems. I have no trouble imagining that computers are going to start becoming better at proving theorems than human beings are. Computers are better at playing chess and Go than human beings are. Proving theorems is kind of in the same direction. But doing math is so much more than that, because doing math involves asking the questions in the first place. Like, what if I put this thing together with that thing? And physics is very similar. What if I think about this particular system in a completely new way? They're not well-defined problems. And those are the areas where computers are not as good. Maybe they will get there. I have no doubt that in principle, a computer can be just as good as a human being. But because we human beings don't even understand what's going on when we make these creative leaps, it's hard for us to train the computers to do it. So in my lifetime anyway, I don't think that my job is in danger of being put out of work by the computer revolution. There's so many questions that are easy to ask and hard to answer. People ask me on my podcast, if you just be having one physics result from the future told to you, what would it be? Well, I want to know the theory of everything, right? Like, is that cheating? Is that not giving an unfair answer? I want to know everything. But if you want to narrow it down to like one aspect of everything that would be better to understand, I want to understand how to reconcile quantum mechanics with gravity, right? I want to understand what quantum mechanics itself actually says and how gravity emerges from that. I have some ideas about it. We're working on it, in our day jobs. But I suspect that there's something deep that we haven't yet guessed at yet. And that's going to be related to a bunch of other questions like what happened at the Big Bang? What happens inside black holes? There's many other questions you could ask, but that's one group of questions that everyone recognizes is really important. We're all thinking about it very hard, but we don't know the final answers yet.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.